Okay, just want to update you guys with the progress on the chronograph. So I now have the PCB laid out and sent out for fab. Just to give you an idea of what the circuit looks like, this is the oscillator circuit that I designed previously in the previous video. So basically, the oscillator here is made out of this transistor Q1, and it feeds the coil through these two header pin. So that's the second coil here, and then it also feeds the first coil with the two header pins here. The oscillator is also feeding the synchronous demodulator here. The output of the coils, the two coils, the second coil here and the first coil here, feed through a differential amp, through a bandpass filter, through a synchronous demodulator, and then outputs through a low pass filter with this RC here. And I also added a latch to strobe the LED when it detects the bullet through the coil. So looking pretty good. Can't wait to get the board fully populated and test out. Another thing is the sensors. The two coils are spaced exactly 6 inches apart. So the coil will be mounted here and here. I will probably do some 3D printing for this PCB so it can mount directly onto the rail. So I have further improved the sensitivity of my chronograph. Basically, it can now detect a fraction of the change in inductance. I'm able to now detect about 0.034 microhenries of change in inductance. That's about 1.1% of the total inductance. That's pretty sensitive. I'm running the simulation right now of the response, and the PCB layout that you just saw is this updated circuit with improved sensitivity. Here you just saw the bullet entering the first coil, which is L1 here, and then it will enter the second coil, which is L2, and the change in inductance is only 0.034 microhenry. And there you go. As it enters the second coil, it triggers. Pretty good response now. I got rid of the false trigger in the previous version of the circuit. So as soon as you power up, it's pretty quiet, and then when the bullet enters the coil, it will, give a pretty good clean pulse, and the time between the two pulses is approximately 49.28 microseconds. So if I space the two coils at approximately 8 inches apart, this could easily detect a bullet going like 13,000 feet per second. So it's pretty fast and pretty sensitive. That's it.